Hello. In this video, we will be covering Chapter 3, Functions, and we're going to focus on Section 3.1, Functions and Function Notation, and this is Part 1. This section will be broken up into 2 lecture videos. So what we're going to be learning are the following objectives. Specifically, in this video, we're going to focus on determining whether a relation represents a function and finding the value of a function. The other 3 objectives we will cover in the next video. So, let's start with some vocabulary. A relation is a set of ordered pairs. So when we think of ordered pairs, think of something like this. The ordered pairs 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. Each of the ordered pairs has an x value and a y value. So in the case of the first point, 1 is the x and 2 is the y. So in a relation, which again is a set of ordered pairs, the set consisting of the first component of the ordered pairs, the x's, that's called the domain. And the set consisting of the second component of each ordered pair is called the range. So if you give the set of all of the x's, that's the domain, and if you give the set of all of the y's, that is the range. So in this case, the domain of the relations above here, the relation of ordered pairs, is the set of numbers that are 1, 2, 3, 4, and 5. So all I did was listed the x's. The range, that is the set of y's. So the y's, or the output values, are 2, 4, 6, 8, and 10. So in this case, the range is 2, 4, 6, 8, and 10. So that brings us to function. And again, this is what this whole chapter is about, is functions. So a function is a relation that assigns a single element in the range to each element of the domain. What that means is each input can have only one output. Each x can only have one y. I'll write that down. Each x can have only one y. So consider the following. If we have an ordered pair, a set of ordered pairs where they're not all specifically numbers, but we have the words even and odd as the input variable. So odd 1, even 2, and then the next one would be odd 3, and the next one would be even 4, and the last one would be odd 5, and this is our relation. So in this case, each element in the domain is assigned to multiple elements in the range. look at it this way. The word odd. It was attached to 1, 3, and 5. So it got associated with 3 different Y's, 3 different output variables. The word even, it's associated with 2, 4, and 5. So in this case, the input variables have more than one output variable, which means in this case, this would not be a function. It is a relation, but it is a relation that is not a function because, again, each x or each input variable had more than one output variable. So again, to be a function, the relation can only have one element from the range for each element of the domain. So each input can only have one output. So let's look at this example and let's decide whether each of these represent functions. Now, these are all relations, but they look kind of funny. This is a relation. It is a set of ordered pairs, but it is written in a mapping format. So let me just show you what I mean by that. So for A has the ordered pairs P, M, because P goes to M, so input, output. And then the next one would be Q, N, and the last one would be R, N. So in this case, P is only mapped to M, Q is only mapped to N, and R is only mapped to N. Now, Q and R both are mapped to the same letter. However, Q isn't mapped to 2 different letters. Q, which is the input, is what matters. The output can be mapped to multiple inputs, but the input can only be mapped to one output, if that makes sense. So Q is only mapped to N, R is only mapped to N, so that means that this is a function. All right, so let's look at B. We have the ordered pairs PX, QY, and RZ. So again, P is only associated with X, Q is only associated with Y, R is only associated with Z. So again, this would be a function. All right, let's look at C. We have the point PX right there, and then we have the point QY, and then we have the point QZ. So in this case, check it out, P is only associated with X, but Q is associated with not only Y, it's also associated with Z. It's kind of like saying, thinking of it in real world terms, it's kind of like Q is having a relationship with 2 different partners. Q is in a relationship with Y, and Q is in a relationship with Z, and that is against the rules, at least to be a function. So in this case, this relation for C is not a function because Q is associated with Y and with Z. So just to review, a function is a relation in which each possible input value leads to exactly one output value. So 1 X for 1 Y. So we say the output, this is important here, the output is a function of the input. So just for later on, this is a way that we talk about functions. And we always say that the output is a function of the input. So this is the same thing as saying the y is a function of x. So think about it that way, because output is y, input is usually x. And this will come in handy later when we are trying to write things in what is called function notation. Also remember that the input values make up the domain and the output values make up the range. So we want to know how to, given a relationship between two quantities, determine whether the relationship is a function. Now, we've already been doing that up here. We saw that this first one, the odd and even one, was not a function. And then we looked at these three and we determined the first two were functions and the last one was not a function. But what was it that we were doing? What are the steps? So here they are. So step one, identify the input values, the x's, and then identify which ones are the output values. Now, please note that often it will be written as ordered pairs, but ordered pairs can also be written in a table format, which we'll see later, and a mapping format. Later, we'll also see functions written in an equation format. We'll also see it graphed. So, but if we're looking at a table format or ordered pair format or a mapping format, we can just identify the input and the output values. And then if each input value leads to only one output value, then we classify the relationship as a function. So if any input value leads to two or more outputs, do not classify the relationship as a function. So basically, when you're looking up here at these, check out just the x side. What do you notice? So if we're just looking at the inputs, in the first set, the inputs are all different. And the second one, the inputs are all different. And the third, the inputs, there are a couple that are the same. So if the inputs repeat, it is not a function. That's if we're looking at it as a set of ordered pairs. Okay, so now we're going to look at some real-world scenarios of functions. So example 1, determine if the menu price lists are functions. The coffee shop menu shown below consists of items and their prices. Is price a function of the item for part A? And part B, is the item a function of the price? Well, that kind of sounds like the same question. But if you notice, the wording is ordered a little different. In this case, we're saying, is price a function of the item? And the second time, we're saying, is the item a function of the price? And we have to look at these a little bit differently. So let me just kind of show you how to set these up. So for part A, I'm going to have an input. I'm just going to make this, put it in a table format, because I feel like it's a little bit easier that way. So in this case, the input, so when they say, going backwards, I just want to remind you, up here I highlighted it. The output is a function of the input. Output is a function of the input. So the way they worded that, if we say the output is a function of the input. So in this case, price is output and item is input. It all has to do with the order they worded this question in. So is output, or the price, a function of the input, which is the item? So in this case, let's write above here that this is the item and this has to be the price. Now, notice this when I'm setting up this table, this was second, this was first, even though in the sentence or in the question, the word price comes first and the word item comes second. So you don't necessarily set up the table in that order. So again, is y a function of x? Is output a function of input? Is price a function of item? So item comes first, price comes second. So the items were donuts. So we have plain, we have jelly, and we have chocolate. And then the prices are $1.49 for the plain, $1.99 for the jelly, and $1.99 for the chocolate. So is this a function? So remember, to determine if something is a function, each input value leads to only one output value, which means the inputs can't repeat. So a plain donut is always $1.49. A plain donut doesn't have any other price. It's always $1.49. A jelly donut is always $1.99. A chocolate donut is $1.99. And it doesn't matter that jelly and chocolate cost the same as long as jelly only has one price. It doesn't have two different prices. It has one price. Chocolate has one price. So in this case, is price a function of the item? Yes, it is a function. Now let's look at B. In this case, it says, is the item a function of price? So remember, is the output a function of the input? So in this case, input or the x's, output or the y's. In this case, that would be the input this time is the price. So the price is on the left and the item is on the right. So this time we start with the prices. So we have the price $1.49, which is a plain donut for the output. Then we have the price $1.99, which is a jelly donut. Is everybody getting hungry? And then $1.99, which is a chocolate donut. Okay. In this case, the price $1.49 is only associated with plain, so that's good. But the price $1.99 is associated with both jelly and with chocolate. So $1.99, if that is the input variable, it is associated with two separate output variables. So in this case, is the item a function of the price? No, it is not a function. And it is not a function, again, because $1.99 has two separate output variables. All right, so let's look at example 2. We're still determining whether a relation represents a function. So determining if class grade rules are functions. So this is a little different because this is ordered pairs, but it's more ordered pairs than what you realize. Okay, so let me just show you what I mean before we go into the question, which is grade point average a function of percent, and is percent a function of grade point average? So if you want to look at this table here, and we want to write this as ordered pairs, what's really going on is, okay, so if we said the percent grade and then the grade point average, the GPA, so this here is 57 different ordered pairs. It's 0, a percent grade of 0 has a GPA of 0.0, a 1 has a percent grade, or a 1% grade has a GPA of 0.0, A grade of 2 has a GPA of 0.0 all the way. We keep going until we get to 56, which has a GPA of 0.0. Then we just keep going, and I don't want to write all those numbers, so I'm just going to start back up here. Then this next one, 57 through 61, so we have 57, 58, 59, 60, 61. All of these are 1.0s. And if you look at the next one, 62 through 66, so 62, 63, 64, 65, 66, all of those were 1.5s. Okay, so hopefully you can see that this is a whole lot of ordered pairs. This is like 0 to 100 would be 101 ordered pairs. And no, we do not have to list all of that. Okay, so let's answer the questions here. So in the first one, it says, is grade point average, GPA, a function of the percent grade? So in this case, is output a function of the input? So this is your X and this is your Y. So this is set up, percent is the X. So this is set up kind of how I wrote it here, and this is the Y. So if we're looking at that, if you look at these, 57 is only a 1.1, 1.0. 58 is only associated with a 1.0, 59 is only associated to 1.0, skipping down, 65 is only associated with a 1.5. What this means is each percent grade is associated with only one GPA. So you can't make, let's say, a 63% and have two different GPAs. You only have one GPA, and that's a 1.5. So in this case, that makes that a function. Yes, this is a function. Now, if we reverse it and we say, is the percent grade a function of the GPA? So in this case, the percent grade is the output, and the grade point average is the input. So basically, we're reversing this. So in this case, we have GPA coming first, and then we have the output, which is the percent grade. So let's just take, we'll just take this part. Now, instead of listing the whole thing, I'll just take part of it. Let's just look at this part. So in this part, we have the point 3.0 is a 78, 3.0 is a 79, 3.0 is an 80, all the way down to 3.0 is an 86. And just looking at this, you can see that 3.0 is associated with multiple, not just two, definitely not one, not two, not three, but multiple percentages. So because the 3.0 is associated with multiple percentages, and not only that, 2.5 is associated with multiple, 2.0, 1.5, all of them. Each of the X's, or each of the inputs, in this case, if the input is GPA, they're associated with multiple outputs. And remember, you can't have that to be a function. So in this case, no, it's not a function. And if they ask why, you can just pick. You can just pick one of the X's that are mapped to multiple Y's. Pick one of the inputs that are mapped to multiple outputs and give that as your reason. All right, so your turn. This is a try it. So that means it's your turn. So the table lists the 5 greatest baseball players of all time in order of rank. So you want to do part A. Is the rank a function of the player's name? And is the player's name a function of rank? So what we want you to do is pause the video, try part A, try part B. When you're finished, click play, and we'll go over the answer. All right, go ahead and hit pause. All right, hopefully you had hit pause and you tried this problem. So let's look at part A. Is rank a function of the player's name? So rank would be the output. I'm going to write OP for output, and the player's name is the input. So we're doing player's name first and rank listed second. So basically the way that this is already set up. So Babe Ruth only has one rank 1. Willie Mays has only one rank, 2. Ty Cobb, only one rank, 3. Same for Walter Johnson. Same for Hank Aaron. So each X or each input has only one output. So yes, this is a function because each input variable is associated with only one output variable. Now let's look at part B. And I went ahead and so in this case, the player's name, we're trying to see if that's a function of the rank. So in this case, the player's name is the output and the rank is the input. So it's reversed. So you notice I went ahead and reversed it and put the input, which is rank here, and the output, which is player, the way it's written in the question. So 1 is only associated with Babe Ruth. 2 is only associated with Willie Mays. 3 with Ty Cobb. 4 with Walter Johnson. 5 with Hank Aaron. So in this case, yes, it is a function. So A is a function. B, is also a function. So in this case, it didn't matter the order. It was a function either way. All right, so now we're going to talk about function notation. Function notation. So when we talk about functions, we often use a different type of notation, and you may have seen this notation before. So function notation, the notation y equals f parentheses x defines a function named f. This is read y is a function of x. So when you see f parentheses x, we say f or the function of x. We also may say f of x. X represents the input value and the y represents the output value. We also call input values independent and output values, we also call those dependent variables. So we don't always use f. So in this case, we call the function f. We use other letters like G and H and M. So an example would be the function h of a. So in this case, that might represent height is a function of age. So oftentimes we'll use variables that are associated with what they represent. So H for height, A for age. But this, again, goes hand in hand with the wording we saw up here. Let me go back to it, where we said that the output, right here, the output is a function of the input. So the y is a function of the x. And that is, honestly, that is how we're writing it down here. H is a function of A. Height is a function of age. Actually, I'm saying that wrong. So let me just correct myself. If we had, let me write it this way. H equals a function of age. There we go. Write it like that. Sorry. But again, you still might see, a function written like that, h of a, which still might represent height as a function of age. So, let's see. So if we have example 3, a function n equals f of y gives the number of police officers in a town in year y. What does f 2005 equals 300 represent? So in this case, they're saying n, oops, I meant to highlight that, not scribble it. N is the number of police officers. Okay. Y, I'll do a different color. Y is the year. And that kind of makes sense. N for number, Y for year. So what does F 2005 equals 300 represents? Well, in this case, the number of police officers is a function of the year. So in this case, in 2005, there were 300 police officers. So note that the inputs to a function do not have to be numbers. Now, we talked about that before when we were using the words even and odd, and then we had Babe Ruth and the other baseball players. Function inputs can be names of people, labels of geometric objects, or any other element, etc. That determine some kind of output. However, most functions that we're going to work with are going to be numbers as inputs and outputs most of the time. So moving on to example 4. So use function notation to represent a function whose input is the name of the month and the output is the number of days in that month. So for this one, we want to write the function notation for this word problem. So in this case, it says the input is the name of the month and the output is the number of days in that month. So remember that output is a function of the input. Okay, so just keep saying that to yourself over and over and over again. That's going to help you so much with this wording. So the output in this case, output is the number of days. So we need to think of a letter to represent the number of days, and I think I'll use D. Is a function of the input. And in this case, the input is the name of the month. So I'm gonna use M. So you can actually write it out in words. So the number of days is a function of the month. So in this case, let's use input variable. Let's say our input is January. So in this case, the function of January is capitalized. So the function of January is equal to the number of days, and the number of days in January is 31. The function of February, that would be, if it's not a leap year, that's 28. All right, so it is your turn again. Use function notation to express the weight of a pig in pounds as a function of its age in days, D. So pause the video, try to write this out as a in function notation, and then unpause it when you're finished and see how you did. Go ahead and hit pause. Okay, so hopefully you had time to write this out. You paused the video and now you've unpaused it. So use function notation to express the weight of a pig in pounds as a function of its age. So remember, output is always a function of the input. And the input is what goes in here. So the output, this may help you, is always a function of the input. That might help you to write it like that. So in this case, the weight in pounds, so I'm just going to use P for pounds, is equal to the function of A. Or actually they said age in days, D, so we'll use D. We'll use D instead of A. So you could write it in words. Weight is a function of age in days. You could write it like that. All right, so I've been doing this already. As you can see in some of these older ones that I did, we wrote things in table format. So we're just going to continue talking about that now officially, representing functions using tables. So check out these three tables that I have here. So this first function, this is the function of the number of days is the function of the month. So the number of days, D, is a function of the month. So in this case, we use numbers to represent the months. So month 1 would be January, month 2 would be February, 3 would be March, so on and so forth. So if you said the function of 12, so that's December. So the function of 12. So how many days are in December? There are 31. If someone asked you, is this a function? Is it a function? Because technically, just because it's set up as a table of values which represent ordered pairs, that does not mean that it is a function. So let's just go ahead and check. So January always has 31 days. February always has 28. Now, let me specify, this table represents the months when it's not a leap year. Okay, because obviously February could be 28 days or it could be 29 days depending on the year. So let's pretend that this table represents a non-leap year. So in this case, February is always 28 days, March is always 31. So yes, this is a function. The domain of the function is 1 through 12, and then the range is basic. Oh, let me just show you this. So the domain are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then the range, that one, you do have a lot of numbers, but you don't have to list them all separately because some of them are the same numbers. So we have the numbers 28, 30, and 31. So you can just write the range like that. All right, so let's look at the next one. This is function G. This is function G. And so instead of calling it function F, we're calling it function G. So in this case, Q is a function. Oops, I just said this is function G, and look what I wrote. I wrote F. Function G. So Q is function G. So Q is a function of N. I don't know what N or Q represent, but Q is a function of N. In this case, is this a function? Well, I'm looking, all of the x's, none of those repeat, so yes, that would be a function. And then for the domain, you could just list the numbers 1 through 5, and then for the range, we can list the numbers 6, 7, 8. All right, so let's look at age in years as the input, height is the output. So in this case, if it were a function, we would say height is a function of age. However, upon a study of this particular relation, check this out. 5 is associated with 2 different output variables. So this is a relation that's actually not a function. Okay. So let's continue talking about representing a function using a table. So if you're looking at a table, make sure you identify the input and the output variables. And if you're trying to determine whether it's a function, check to see if the input variable value is paired with only one output variable. So in which case the table is a function. So let's look at example 5. And it says identify tables that represent functions. Which tables represent a function, if any? So in this case, 2 is only mapped to 1, 5 is mapped to 3, 8 is mapped to 6. None of those seem to repeat, so this is a function. -3 for the second table, -3 maps to 5, 0 maps to only 1, 4 maps to only 5. So even though -3 and 4 both map to the same number, the inputs themselves are only mapped to one number. So what that means is -3 isn't mapped to 2 numbers. 4 isn't mapped to 2 numbers. They're each only mapped to 1. So that means that it is definitely a function. Let's look at the last one. 1 maps to 0. 5 maps to 2 and up. 5 also maps to 4. So in this case, because 5 maps to multiple output variables or values, rather, it means that it is not a function. All right, so your turn. Try it. So we're going to look at this possible function, this relation, and determine if it represents a function the way it is written. So go ahead and pause the video. And then when you are ready to check your answer, hit unpause. All right, so you've unpaused the video and you're checking your work now. So let's see if this is a function or not. The input value of 1 only maps to 10. The input value of 2 only maps to 100. The input value of 3 only maps to 100. I'm sorry, 1,000 rather. So that means that each x is associated with only one y. So that means it is a function. And look at that, your teacher has forgotten how to spell function. I spelled function because I think math is fun. Don't you think math is fun? You're saying this lady is weird. All right, so yes, it is a function. All right, now this is the fun stuff. This is where we get to the actual calculations and crunching numbers. So more than just yes or no answers or listing domains and ranges, finding input and output values of functions. So notice this, we're not just finding output values, we're also finding input values, not at the same time, but we will be finding both. So how to do this? Given the formula for a function, so we can list functions as an expression attached with an equal sign. So basically kind of like an equation format. And so when you're doing this, you basically, when they say evaluate, they will give you a value that they want you to evaluate the function at. So basically what they're saying is when the x value is this, what would the output value be? So we're going to substitute the input variable that they give us into this formula, and then we're going to calculate the results. We're going to make sure that we use all our math rules and our orders of operations and all of that fun stuff to get there, but basically we're just substituting in numbers. So we are evaluating the function f of x equals x squared plus 3x minus 4 at the following x's. So the input variable in this case is x. So each of these numbers down here, a, b, and c, those represent x's. We'll talk about kind of what d means in a moment. So let's do the first one, f of 2. So we're replacing 2 with x. So I said that backwards. We're replacing x with 2. So I'm going to rewrite the equation, and I'm going to write it with parentheses instead of the variable. So parentheses squared plus 3 parentheses minus 4, and inside the parentheses I'm going to replace it with the value that I'm evaluating the function at, which is 2. Kind of write it in green over here too. Now first, hopefully you know this already, but first I want to make sure that you know that f of 2, the function of 2, means evaluate the function at 2. It does not mean f times 2. So please do not say that this is 2f. It is not 2f. It means the function evaluated at the value of 2. So when the x is 2, what is the function equal? So you're not doing anything over here on the left-hand side. You're only going to do calculations on the right-hand side. So over here, I'm going to do the exponent first. So 2 squared is 4. Next, I am going to do multiplication. So 3 times 2 is 6. So 4 plus 6 minus 4. At this point, I'm looking and I see that the 4 and the negative 4 cancel each other out, and that just leaves 6. If you had wanted to go through it, 4 plus 6 is 10. 10 minus 4 is 6 that way. So in this case, f of 2 is equal to 6. And this here, let me change that, is the function notation for that. But I just want to make you aware that this is the same thing as saying when the x is 2, the y is 6. This is the same as writing the ordered pair 2, 6. It's the same thing. Okay, let's do the next one. I'll do it in a different color. So this was A. So now we're going to do B. So B, we're finding f of x is equal to x squared plus 3x minus 4. And in this case, we are replacing the x's with A. So this one's actually pretty easy. Again, don't multiply f times a, it's just f of a. A squared is just a squared. 3a, or 3 times a is just 3a. That leaves minus 4. So there you go. That's it. You can't go any further. You can't add a squared plus 3a. We're actually done. So if you wanted to write it as an ordered pair, when x is a, then the y is a squared plus 3a minus 4. However, I know that looks kind of funny. This is, you'd actually most likely leave that in function notation. All right, let's try C. C, we're substituting in a plus h. So we have to really remember some of our math skills here, these rules. So x squared plus 3x plus, nope, not plus, minus 4. All right, and we are substituting in A plus H. Oh, so we have, let me expand it a little bit. F of A plus H is equal to A plus H squared. So I'm actually going to go over here to the side, and I'm going to do A plus H squared, and just kind of remind you how to do this. Now, this is a perfect square, so you may remember the perfect square formula. This would be A squared plus 2AH plus H squared. However, if you don't remember that, let me just show you kind of what I did here. A plus H squared is not A squared H squared. It is A plus H times A plus H. And this is where we distribute the A to both terms of the second parenthesis, and then distribute the H to both terms of the second parenthesis, and then we add any like terms. Many of us fondly know this as the FOIL method. First, outer, inner, last. Makes a little smiley face right there. So if you multiply A times A, you get A squared. Then you distribute A to the H. That's outer. A times H would be AH. Then you, once you've distributed the A to the A and then to the H, we're now going to pick up and we're going to distribute the H to the A, which would be HA, which is the same as AH. And then we'll distribute the H to the H and get H squared. And then in the middle are our like terms. They're both AH's, because H times A is the same as A times H. So you have A squared plus AH is 2AH, and then again H squared. So A plus H squared is A squared plus 2AH plus H squared. Then we have the 3 times 8 plus H. So we're going to distribute the 3 times the A and then the 3 times the H. So that gives us 3A plus 3H. And then we're just going to bring down our minus 4. So in this case, we have F of A plus H is equal to A squared plus 2AH plus H squared plus 3A plus 3H minus 4. So basically what we had written right above, and I can't go any further because A squared, there's no other A squared to add it to. There's no other AH. There's no other H squared. There's no other A. There's no other H by itself. And there's no other negative constant like negative 4. So that's as far as we go. All right. So kind of section off this last part here. So the last part we have FA plus H minus FA over H. So let me... FA plus H, F of A plus H is here. So I'm going to go ahead and write that. That's A squared plus, this is D by the way, A squared plus 2AH plus H squared plus 3A plus 3H minus 4. And then we're subtracting F of A, which we also found F of A is part B. That was A squared plus 3A minus 4, all of that over H. So, since we are subtracting, we're subtracting each of these values in the second parentheses. So we are, so I just want to take this away here. And we're basically, what this means is we are subtracting the A squared, we're subtracting the 3A, and we're adding the 4. And then what happens is that, oops, I forgot my bar here. The A squares cancel. I should do this in a different color. The A squares cancel. And then what else cancels? The 3A minus 3A, that cancels. And the negative 4 plus positive 4, that cancels. So that leaves your 2ah plus h squared plus 3h, all of that over h. And then if you divide h into all three, the h cancels out of all three terms. That leaves 2a plus h plus 3. So there you have it. F of a plus h minus f of a over the whole thing over h. All right, so let's move on. All right, let's look at example 7. In this case, they only want us to substitute in negative 4a and negative a into this equation, or this function here, p squared plus 2p. All right, so let's try these. Let's try h of negative 4. So in this case, I'm going to rewrite the equation, p squared plus 2p, except I'm going to replace the p's with negative 4. And in this case, h of negative 4 is equal to negative 4 squared, which is 16. 2 times negative 4 is negative 8. And then 16 minus 8 is 8. So h of negative 4 is equal to 8. All right. Let's do the next one. We have h of a, and then we're just going to replace a everywhere we see p. So a squared plus 2a, and then you're pretty much done. That's as far as you can go there. There's nothing else you can do there. All right, so let's look at the last one, h of negative a, and we have negative a replacing the p. So h of negative a is equal to negative a squared would be a, because negative times negative is a positive, plus 2 times negative a would be negative, oops, I forgot the square there. Negative a squared would be a squared, minus 2 times negative a would be negative 2a. And you can't go any further than that. So that was the second one. And this, oops, this is the third one. All right, your turn again. Given the function g of m equals m minus 4, go ahead and try to solve it or evaluate it. By the way, hit pause first. Okay, so you've unpaused. Hopefully you have worked through this try it. So we're trying to do g at 5, square root of m minus 4, and instead of m, we are replacing that with 5. So g of 5 is equal to the square root of 5 minus 4 would be 1. And then the square root of 1 is 1. Okay. All right. Now I told you we were finding input values and output values. So far we have been finding output values by substituting in input values, but now we're going to find input values by substituting in output values, and it requires a little bit of a different approach because you're substituting it into a different part of the formula. So instead of evaluating it and just using orders of operation to calculate the answer, now we're going to actually have to solve an equation. So that's a whole nother set of rules that we would need to remember how to do. So in this case, we have h of p, which is p squared plus 2p, and we are substituting in 3 for h of p. We're not substituting it in for p, we're substituting in for h of p. This is kind of like saying y equals 3 if the equation was y equals, we'll just say x squared plus 2x. It's kind of like saying the y is 3 and substituting it in. So we're going to put 3 in for h of p. Notice the whole thing, h of p goes away, it becomes 3. We didn't say h parentheses of 3. That's different. Okay, that's if the p was 3. In this case, the whole function h of p equals 3. And in this case, we want to use that to find what p is. All right, and of course they start off with an equation that's not linear. So this is where you get to remember how to solve by factoring or the quadratic formula. So anytime you have a quadratic, that means you've got a variable that's squared. That's the highest exponent that you have in the problem, and it's on your variable that you're trying to solve for. That's a quadratic, right? So you have a couple different ways to solve. All are ways that you should have learned prior to now, but if not, that's okay. You can pause this video. You can go back and look in the earlier chapters, chapters 1 and chapter 2. You can send me an email and we can talk about it. How do you factor? But I'm going to go through it really quick with you and show you how to do it. So you can solve these kind of problems by factoring. You can also use quadratic formula, and then some of you may have learned completing the square. Always fun. So you have options. You can also solve it by graphing. But again, you have lots of different avenues that you can go down to actually solve this problem. However, I'm just going to focus on what I think is the easiest way to solve that, and that would be factoring. So anytime we have a quadratic, most of the time what we do is we want to get 0 on one side. So I'm going to subtract 3 on both sides, because what you do to one side, you do to the other. So instead of trying to get the variable by itself in the beginning, we try to get the whole equation on one side and 0 on the other. So we have 0 equals, now notice I kind of just threw the minus 3 over all the way to the right, and that's because it's not a like term with anything. So in this case, 0 equals p squared plus 2p minus 3. And at this point, you can choose to do the quadratic formula for those that want to remember what I'm talking about. Negative b plus or minus b squared minus 4ac over 2a. X equals, in this case, p equals. Okay. But again, completely different lesson. And I'm not going to go that route. But you can. If you remember how to do it, you can go that route. I'm going to factor again. So in this case, what I want to do is I want to write this as two factors, two binomial factors. Binomial means two terms in each. And I'm kind of doing backwards FOIL. So to get this first term right here, what do I multiply together to get p squared? And that'd be p times p. And then for the last one, this will be, what are the numbers that you can multiply together to get negative 3? That's what you're going to go there. However, it is, what do you multiply together to get negative 3? But at the same time, you have to add it up. And those same two numbers you add up, and you get this middle number, which is 2. So what do you multiply to get negative 3? Add to get 2. And let's see, if I multiply 3 times 1, I'll get positive 3, but I want negative 3, so let's make one of them negative. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. I don't want negative 2. So let's try it again and make the 1 negative. 3 times negative 1 is negative 3. 3 plus negative 1 is 2. So there we go. Those are our values that go here. So positive 3, negative 1. You want to check it. You don't have to, but I'll just show you that we are correct. If we FOIL this out, you get p squared, negative 1p, 3p, negative 3, add like terms in the middle, and we get what we got right there. So yay. All right, so that's taking up all my, I'm just going to erase it. Okay, so going back here, erase all that too. All right, so now we have 0 equals p plus 3 times p minus 1. And so the reason we did this, we wrote this as two factors because we know that when we multiply two numbers together, and if we know that the answer is 0, as it is in this case, we know that one of these factors here, either this one right here or this one right here, has to equal 0. So either p plus 3 equals 0 or p minus 1 equals 0. So in this case, if p plus 3 equals 0 and we solve for p, subtract 3 from both sides and you get negative 3. If p minus 1 is what is actually equal to 0, then to solve that, you add 1 to both sides and you get p equals 1. So p equals negative 3 and p equals 1. So in this case, we have two solutions. There are two different p's that will give us 3. If you put in negative 3 into this original function, and let's just check it just to make sure. Go back to the original function. If we have h of negative 3 is equal to negative 3 squared plus 2 times negative 3. So negative 3 squared is 9. 2 times negative 3 is 9 plus negative 6. 9 plus negative 6 is 3. If we substitute in the other number, we got 1. 1 squared plus 2 times 1 would be 1 plus 2, which is, again, 3. So it checks out the answers, two different answers, but we still get two answers. They are negative 3 and positive 1. So you give it a try. This time we're giving you g of m right here. And g of m, if you will recall from the earlier, I think from example 7 that we did, No, from the last try it, actually. It was the last try it, not example 7. So from the last try it, remember that g of m equals square root of m minus 4. We're going to put in 2 for the g of m, and you're going to solve it. So this will require you to kind of think back and think, how do we solve equations that involve square roots? So pause the video, and then when you unpause, we will go over it. Okay, so hopefully you went over this problem, or you tried to work it. So now I'm going to substitute the g of m. I'm going to replace that with 2 is equal to the square root of m minus 4. And then what we're going to do is we're going to undo the square root. And so to undo the square root, you are going to square both sides. And we get 2 squared, which is 4, is equal to the square root of m minus 4 squared is m minus 4. So in this case, we add 4 to both sides. M equals 8. And if you want to check it, 8 minus 4 is 4. Square root of 4 is 2. So, yes, that works. Okay, moving on. So this is just giving you the steps of what we've just done. So evaluating functions expressed as formulas. So given a function in an equation form, write its algebraic formula. And then solve the equation to isolate the output variable on one side of the equal sign and the other side as an expression that involves only the input variable. Use all the usual algebraic methods for solving the equation, such as adding, subtracting the same quantity to and from both sides, or multiplying or dividing both sides of the equation by the same quantity. So things that we just did. The only thing that we haven't done yet is if we're given the equation if we're given the function in equation form, how to write it in algebraic form instead. So, but we're going to use kind of what we did up here, some of the solving we did. So, in this case, express the relationship 2n plus 6p equals 12. So actually, this is kind of algebraic format, and they actually want us to go backwards to the function format. So we want to write this like this. Express it as a function p equals f of n. So going back up to these steps, so I apologize. I think I told you this was a summary of what we did up here, but this is actually showing us how to do something new. So in this case, we want to write this as a function. So the first thing you're going to do is you're going to isolate the output variable. So in this case, the output variable is here. Remember, the output is a function of the input. So we're going to get p by itself. That's the first step. So we will use some of the skills we used earlier when we were solving equations. It's just going to get a little bit more complicated, or not really complicated. We just have to remember more rules. So we want p by itself. So notice I drew a line down the equal sign so that I can see there's a left side and a right side, and it says isolate the output variable. So I want to get p by itself. That means I want to get rid of this whole term here, 2n. And to do that, I subtract 2n on both sides. So, excuse me, on the left-hand side, the 2n and the negative 2n cancel, and that leaves 6p is equal to this side, 12 minus 2n, and you can't go any further on the right-hand side because they're not like terms. Now, you could have also written it this way. It's the same thing, okay? Either way, you're going to end up with the same thing. So again, we're trying to get p by itself, so we need to get rid of the 6. So to get rid of the 6, we're going to divide both sides by 6. So on the left-hand side, the 6's will cancel. 6 divided by 6 is 1, and that just leaves 1p, which is p. And on the right-hand side, you need to divide the 6 into both terms. So 6 will go into 12 twice, and it does not go into 2, so that would leave 2 over 6n, or 2 minus, we could reduce it to 1/3 n. So we wanted to express the relationship in this format. So in this format, we have p is equal to f of n, which equals 2 minus 1/3 n. And that's really all they wanted us to do there, is to basically solve it for n and then write it as a function. All right, so let's try another one. Consider the relationship 3r plus 2t equals 18. We're going to write the relationship as a function r equals f of t. So r, the output, is a function of the input t. So in this case, r is what we want to solve for. So 3r plus 2t equals 18. Draw a line to show the two different sides. Subtract 2t from both sides. That leaves us with 3r, because the 2t's cancel, equals 18 minus 2t. Divide everything by 3, and we get r is equal to 3 will go into 18, 6 minus 2/3 t. So we would write this, the function of t is equal to 6 minus 2/3 t. You can also write it as the function of t is equal to negative 2/3 t plus 6. That's the same thing. So now when they say find the function at -3, you don't have to substitute it in here. You can actually substitute it into this right there. So 6 minus 2/3 times t, and t we're saying is -3. And when we do that, negative times a negative is a positive, and 2/3 times 3, the 3's cancel and just leave 2. And I believe that we get 8. So f of -3 is equal to 8. All right, so then let's solve f of t equals 2. So that's where we're substituting 2 for t, for f of t. 2 equals 6 minus 2/3 t. We want to get t by itself, so subtract 6. We get -4 is equal to -2/3 t. And we're going to get rid of -2/3. To get rid of a -2/3, you divide both sides by -2/3, which is the same as multiplying by -3/2. And what you do to one side, you do the other. And then on the left-hand side, the 3 and the 2's cancel and just leaves t. I'm running out of space, so I'm going to write it over here. Just leaves t. And then on the left-hand side, -3 times -4 is positive 12 divided by 2 is 6. You can also say 2 goes into 4 twice, and 2 times 3 is 6. Either way, we get 6. So if you're unsure, you can go back and check by plugging either of the numbers into part A and see if you get the other number. You can also go up just to the original equation. Let's see, if we put in -3 for t. So, and so when -3 is t, 8 is r. So 3 times 8 plus 2 times -3. So 3 times 8 is 24. 2 times 3 is 6. 24 minus 6 is 18. Yep, that works. And then let's look at the last one. We have the numbers 6 for the t and 2 for the f of t, so for the r. So 3 times 2 plus 2 times 6. 3 times 2 is 6. 2 times 6 is 12. 6 and 12 is 18. So yay, we got all the parts right. All right, so your turn. Pause the video. Try to express if x minus 8 y to the third equals 0. Try to express express y as a function of x. So go ahead and pause the video, and then when you come back, we will go over it. Okay, so you've unpaused the video. We're expressing y, the output variable, as a function of x, which is the input variable, which means we want to solve for y. So x minus 8y to the third equals 0. So since we're in college algebra, if we were just learning equations, I would subtract x on both sides to get that 8y to the third term by itself, since we're trying to solve for y. But since we're in college algebra, we can manipulate this equation to make it a little bit easier to deal with. So I'm going to actually move this over here. I'm going to add the 8y to the third to both sides, since there's a 0 on the right hand side. That way I make everything positive, you know. So all I did was I added 8y to the third to both sides. All right, now I still want to get y by itself. So to do that, we're going to divide both sides by 8. Now there is an invisible 1 in front of the x that we don't usually write. So we have 1/8 x is equal to y to the third, because the 8's cancel and leave 1y to the third. Now to undo a y to the third to leave just y, guess how we do that? We cube root it. And what you do to one side, you do to the other. So, on the left-hand side, the cube root of 1/8 is 1/2 times the cube root of x equals y. You can also write that as 1/2 x to the 1/3. And the reason is because 1/8 has a cube root, but x doesn't. So, and then we can write our square root in fraction exponents. So that one was a fun one. So, but we're expressing it as a function of x. So, so y equals 1/2 x to the 1/3. That's the same as saying f of x is equal to 1/2 x to the 1/3. All right. So going back to tables. It says, given a function represented by a table, identify specific output and input values. So to do that, we find the given input in the row or the column of the input values and identify the corresponding output value paired with that input value. And if we were finding the given outputs, we just kind of do the opposite. So when they say find g of 2, all they want you to do is go over to 2 and find the corresponding value of the function. So when x is, or when n is 2, g is 6. And then for part B, you're actually going the other way. So when g of n is 7, what is n? N is 3. All right. So for the last one, we are given the graph, evaluate f at -1 and solve f of x equals 0. So it's basically the same thing. You're just going and doing this on a graph. So here they're saying that the f of x, the x equals -1 here. So when the x is equal to -1, they're asking what is the y equal? So when x is 1, the y, I'm sorry, I did that wrong. When x is -1, right? When x is -1, the y is, it looks like 4. When x is -1, y is 4. Okay, now in this case, they're basically saying that the y equals 0. So when y equals 0, what is the x? So here's the y-axis. On the y-axis, we find 0, go over to the x and see what it corresponds to, 1. So x, in this case, equals 1. Okay, so there you have it. That is all we have for part 1 of 3.1, and I know it was a lot. If you have questions, don't hesitate to ask them. Send me an email or post your question on our Padlet wall. Okay? Have a great one.